This is the last one in the series of lectures on sintering of ceramics. In our earlier lecture, we were discussing about the different mechanisms of diffusion which are important for mass transport during sintering. I will briefly go through that once again. There are three main mechanisms of diffusion, namely the lattice diffusion, grain boundary diffusion and surface diffusion. For each of these mechanisms, we have a sintering kinetics, the expression for x by r in terms of time, initial particle size and of course, the temperature. So, they are more or less follow the similar pattern, but with some difference. We were discussing about two or three important parameters here. For example, three diffusion parameters. These diffusion coefficients are obviously different for different mechanisms. For example, d subscript mb, which is ambipolar diffusion coefficient for the material or the compound mx. Then you have grain boundary diffusion d subscript gb, and then surface diffusion or surface diffusion coefficient d subscript s. We also noticed that because this is a lattice diffusion, this is a volume diffusion. So, there is absolutely as such no constraint so far as the area of diffusion is concerned or the area of the flux, whereas in these two mechanisms we have the thin surfaces through which the diffusion takes place, and therefore, the area becomes important. This is our grain boundary area, grain boundary thickness. So, in the cross section it comes as an area, whereas similar is the case with the surface diffusion. We have a term delta sub s, which is the thickness of the surface through which the diffusion is taking place. And of course, in any kind of process, the limiting one is always the slowest species, which is the diffusion coefficient of having the low diffusion coefficient and also along its fastest path. So, these are some of the consideration which we must keep in mind while we are trying to understand the diffusion mechanism of sintering. This we have already discussed. D subscript mb means ambipolar diffusion coefficient for the compound mx, and that is defined because it involves both the cations and the anions, and therefore, the average diffusion coefficient is like this. Then grain boundary width, diffusion coefficient of the grain boundary, surface thickness that we have already mentioned. Now, typical shrinkage behavior we have seen in our very first lecture on sintering. This is almost applies to almost all the diffusion mechanisms, and the kinetics is like this. Delta L is the change in the linear thickness or dimension, and as a function of time, this is normally in the log scale, and we have the temperature effect is there, and as you have mentioned, with time initially the progress or the kinetics is fast and then slows down and becomes almost constant, the rate becomes almost constant, and that initial rate increases as temperature increases and the overall shrinkage, the dimensional change is also larger when the temperature is high. So, these are the typical reaction sintering kinetics behavior of almost all the mechanisms, but the coefficients or the exponent are a little different. While we are talking about the diffusion mechanisms, we should also remember that all diffusion processes are activation, they are activated processes, thermally activated processes, and they have thermal activation energies. So, the activation energies for the 3 different mechanisms, the surface diffusion, grain boundary diffusion and lattice diffusion, are slightly different. In that context, the activation energy for the surface is the lowest, the grain boundary is intermediate, and the lattice surface energy activation energy is the greatest. So, this becomes operative at a high temperature and higher particle size also. This is intermediate temperature and this is at a lower temperature. Surface diffusion is dominant at, that is what is mentioned. The surface diffusion is dominant at lower temperature, while lattice diffusion at the highest temperature. Surface and grain boundary diffusion are preferred for smaller particle sizes. So, this is also another, because smaller particle size means you have a higher surface energy and the surfaces are available in a larger quantity, and therefore, the smaller particle size prefers surface or grain boundary diffusion, when the larger particles always dominates, the lattice diffusion dominates in larger particles. Okay. Now, this is what it means, particularly the comparison of the activation energies for the 3 mechanisms. If you plot log D versus 1 by D, then you have straight line plots. These are the slopes are the activation energies. So, at lower temperature, this is the lower temperature because 1 by T. So, you can see this is the activation energy for the surface diffusion, whereas intermediate one is the grain boundary diffusion, and then the lattice diffusion is the highest, and the activation energy, the slope is also highest, and this slope is lower than this is intermediate. Few more characteristics. Lattice diffusion dominates for larger particle size also, that I have mentioned just now, at longer times and at higher temperatures. So, that is also another characteristics of this lattice diffusion. These general characteristics are not only valid for the initial stage, but also extend to intermediate and final stages of sintering, although we have not analyzed those processes at the intermediate as well as the final stage of sintering. What we have discussed so far is applies primarily to the initial stage of sintering. So, the calculations and the mathematical analysis what has been carried out is primarily based on the initial stages of sintering. However, more or less a similar phenomena or mathematical analysis applies to the other 2 stages, the intermediate stage and the final stage. However, we will not be doing that under this course. Now, we have discussed 2 different mechanisms already. One is the evaporation condensation, and other one we just discussed about the diffusion vacancy mechanism of diffusion. Both are solid state sintering processes. There is one more in that is called the viscous flow mechanism of sintering that we have mentioned earlier. So, let us try to look at it in slightly greater details. As the name suggests, in this mechanism also the particle surfaces get softened at the temperature of sintering, and the mass transport takes place by viscous flow facilitated by the internal stress of the particle aggregate. Okay. Whenever you consolidate particles, they are pressed, either pressed or there is capillary action of the fluid which makes them entangled with each other. So, there is a certain amount of internal stress generated. So, if there is a plasticity available on the surface of these particles at a higher temperature, then this stress is good enough for the flow of the materials on the surface, particularly on the surface. The pores are filled up by the flow of the viscous mass. It is more or less, it is somewhere in between the solid state diffusion and or the solid state mass transport and the liquid state sintering, which we will discuss briefly at after some time. So, it is somewhere in between, the viscous flow is somewhere in between the solid state mass transport or solid state mechanism, solid state sintering and liquid state sintering. The linear shrinkage is expressed as in this manner. Once again, there is a temperature time dependent and it is in fact linearly dependent on time in this case. And the term which is more important here is the viscosity. So far we have not talked about the viscosity of the solid, because it was basically solid state diffusion or evaporation kind of mechanism. Here for the first time there is a liquid involved or a viscoelastic material is involved, and therefore, we have viscosity term has to come in for its flow characteristics. That is another point which I mentioned just now. As in the case of the initial stage of sintering by different mechanisms, rate equations have also been derived for the intermediate and the final stage of sintering by different mechanisms. However, the mathematical analyses are much more complex and more approximate. The exact mathematical analysis is still not available and therefore, we are not discussing it under this course. Well, having discussed the different mechanisms, at least 3 different mechanisms of solid state diffusion, solid state sintering, evaporation condensation, vacancy mechanism and very briefly the viscous flow mechanism. Let us try to look at what happens when towards the intermediate stage or towards the final stage of sintering, how the pore elimination takes place and what are the different driving forces for pore elimination. Pore elimination of course takes place because of the surface energy change, but then at the local level what are the different things happens. Let us try to look at it little more carefully. The assumption that there is always a driving force to shrink the size of the pore throughout the course of the sintering is not always true. We have assumed that there is a extra energy because of the extra surfaces available, and removal of surface will certainly lower down the energy, free energy of the system, and therefore, there will be a continuous removal of the pores because pore removal reduces the surface energy, and therefore, there will be a continuous removal of pore or densification. But sometimes under certain situations it is really does not happen. Under certain situations pore becomes more stable, they do not even get eliminated even if we heat it to high temperature, and because there are some other energy terms which comes in to play. So, that is what it means, that the assumption that there is always a driving force for force to shrink the size of the pore throughout the course of the sintering is not always true. Okay. So, under certain circumstances pore elimination really does not take place. Under certain conditions pore become thermodynamically stable, no further pore elimination takes place. That is the same statement more or less in a different way. Referring to the figure presented in the next slide, we will come to that. The energy gained by the energy lost is equal to this much. I will come back to this in a moment, but let me go to the figure. This is the concept of dihedral angle we have already introduced earlier. It is basically the angle between the tangent of the two surfaces and the tangent and the surface, okay, two tangents of the two different surfaces which is meeting at a particular point or on the particular surface. So, that is called the dihedral angle. Now, here what we have considered as if this is a pore, a kind of, for simplicity we have considered is a rectangular pore. Initially this was the size of the pore, the larger square, actually not rectangle, which is square. So, larger square is the initial size of the pore, and then these are the surface or the boundary between the vapor and the solid. So, this is a grain, this is another grain, and this is another grain, this is another grain. So, there are 4 different grains forming a pore. Okay. Initially this was the largest square represents the pore, and because the pore is shrinking, so it has shrunk after some time, it has shrunk to this distance, this size. So, it is still uniform. Once again, it is an ideal situation, it is still an uniform shrinking has taken place. From the boundary has moved from this to this boundary has moved from this to this, and this boundary has moved from this, and similarly this one. Now, during this thing there is some energy lost and some energy gain. These are the gamma SB, the solid vapor surface energy. Throughout we have solid vapor surface energy, and depending on the area that the total energy should be the surface energy multiplied by the overall surface area. So, while the pore was this much, this was the, considering that there is an unit thickness of this surface. So, this distance becomes, this distance multiplied by this becomes total energy, okay, the total area. And when it comes to this, the area has decreased considerably. So, this energy term has reduced. On the other hand, we have created these grain boundaries. This was not originally there, because there are 4 grains. This, because the pore was so much, so there is no question of this grain boundary, neither this, not this, not this. So, we have reduced the solid vapor area, but we have increased the solid area, that is the grain boundary energy. So, this is the increase in energy, and this is this and this on this side, these two are the reduction in the energy. So, that is what has been mentioned. If this distance is gamma, capital gamma here, and this distance is lambda. Okay. So, this is increase in energy, grain boundary energy has increased, and this energy has been reduced. So, that is what has been mentioned in the earlier expression. So, gamma is the solid vapor surface eliminated, this one has been eliminated, particularly for this corner. Similarly, these corners are also there, 4 corners are there, and lambda is the additional grain boundary area created. This is the grain boundary area created, and this has been eliminated, or this has been eliminated. So, this is for each lambda, 2 gamma area has been reduced. Okay. So, while this much is increasing, this is reduced and this also is reduced. Same is the case in the 4 corners. Okay. So, if you take the that is what is called, referring to the figure present in the next slide, the energy gained is twice the gamma into gamma SB, and then energy lost equal to lambda into gamma GB. Okay. So, this is the ratio of the energy gained to the energy lost. So, combination with this equation, the dihedral angle is given by, while phi is the dihedral angle between these two surfaces. This is grain boundary surface and the solid vapor surface, that is the relationship of the dihedral angle. And based on the fact that cos phi by 2 equal to lambda gamma by lambda from this geometry again, this is the distance, these are the distances, not the angles or energy terms, these are distances basically, geometric terms. This is the lambda and this is gamma, gamma is this one. So, from this this is phi by 2. So, from that this is also phi by 2, and so cos phi by 2 is actually gamma by lambda as per the figure. So, the energy gained equal to energy lost, particularly if the phi is equal to phi, the capital phi and small phi are equal. Okay. So, this is phi cos phi, and the other one is here. Okay. So, if this kind of situation happens, then the two energies are balanced, the energy gained equal to energy lost, particularly if this is this. This means that when a number of grains surround a pore in such a way that lambda GB, the grain boundary energy, equal to 2 lambda SB, solid vapor energy cos phi by 2, the driving force for the migration of the grain boundary and the consequent shrinkage of pores becomes 0. So, no further shrinkage of pores will take place. So, that is another consideration, although we say that surface energy, the reduction in surface energy gains certain energy, and therefore, there will be always a driving force for shrinkage of the pores, but that is not always the case. It all depends on the two terms, what is the value of gamma corresponding to the grain boundary and gamma to the solid vapor. So, depending on that, the dihedral angle changes, and that dihedral angle changes controls whether the pore will shrink or it will stable. For complete elimination of pores, the number of grains surrounding the pore must be less than a certain critical value, NC, that is the NC, such that NC equal to 360 by 180 minus 5. So, this is also important, how many number of sides, how many grains are surrounding a particular pore, that is also an important factor. So, for complete elimination of pores, the number of grains surrounding the pore must be less than a certain critical value. If too many grains are surrounding a particular pore, then there is a less possibility of the pore elimination. So, that also is an important issue while you are trying to see the sintering kinetics or trying to get the theoretical density of a solid. Okay. I will also look at this. This is also a stabilized system, while there are 6 grains, intersection of 6 grains with phi equal to 120 degree. This is also a very stable configuration. Okay. And whenever there is a convex configuration, this is also important, although we have considered here is a plane configuration, but this convex or the concave nature is also important. This is a pore surrounding that. If you have a convex surface of the grains, that becomes more stable than this kind of a situation. Okay. So, this is a more stabler situation than this, and this kind of pores will not be eliminated so easily. Well, we have considered earlier the coarsening of the particles in the very first lecture. There is a possibility of coarsening of particles, and once the coarsening particles takes place at a very low temperature or initial stage of the sintering, then the densification becomes difficult. The grain growth takes place quite fast, and the densification, full densification is not possible most of the time. So, let us try to see how the coarsening of these particles take place, because this has some analogy with the grain growth phenomena which takes place towards the end of the sintering process. After the intermediate stage sintering is over, there is a possibility of grain growth, sometimes called abnormal grain growth, very fast rate of grain growth of certain, not all the grains grow of course, only few grains grow abnormally, and it is order of magnitude, their size becomes order of magnitude larger than the other grains, and that is not a very accepted situation or a satisfactory situation, because if there is a difference in grain sizes, then particularly the mechanical properties gets deteriorated, and therefore, whenever we are trying to sinter a particular material, we need to process the material in such a way, or both the particle size, the agglomeration, and also the temperature rise and all that must be controlled in such a way that there is no abnormal grain growth. Anyway, so the mechanism of coarsening of particles and the grain growth have certain amount of similarity. So, let us try to look at from that point of view. This is the rate equation dr dt, that means the radius of the particle here. These are not pores, okay. These are not pores, these are particles, the solid particles. Okay. So, the rate of change of the radius at a function of temperature of the particle is equal to this kind of a expression AR P average. P is the partial pressure or vapor pressure, and then the vapor pressure of the actual particle at with a radius of r, and this is a kind of average particle size, which can be again represented like this, and 1 by, this is similar kind of equation we have considered earlier as well, 1 by r average, which may be a reference, and this is 1 by r, the actual size. It is given here. The particles smaller than RAV, R average, shrink at the expense of the larger particles which grow. Lower curve corresponds to, okay, there is a plot here dr dt as a function of r, okay, as a function of r, what is the rate of change of the r with temperature. So, this is the rate is positive here, the rate is negative there. So, if you plot this dr dt as a function of r is here. So, we get a curve like this, okay, and this is what we call R average, that is the intersection of this curve with the x axis. This is x axis which is 0, this is positive, that means the particles will grow here and the particles will shrink in this side. The basic essence of this particular equation is any particle having a radius more than this particular value has a positive dr dt. that means it will grow. Okay. So, any particle having this value having value more than this value has a positive dRdt, whether less than this is a negative dRdt. Okay. That is very critical. So, this is either you can call it a average particle size or a critical particle size. You can also say the critical particle size. So, this is what happens if this diameter or this radius and this radius, the average is somewhere here, then this will collapse, this will slowly collapse and the material will getting transferred to the other one and this will grow. So, that is a phenomena of particle coarsening and also a phenomena of grain growth. Okay. This of course says depending on what is the average particle size, which is the critical particle size. In this case the critical particle size is almost double than this value. Okay. So, that depends on the different parameters here. Okay. What is the this value, what is this vapor pressure on the flat surface and so on, and what is the compound, exact compound and so on. So, for any particular system there is always a critical value below which the particles will collapse, will dissolve and the material for that dissolution which go to the other particles having the particle size greater than the critical size. So, that is always a phenomena which is also happens in case of phase transformation like nucleation and growth phenomena, where there is always a critical embryo or critical nuclei size below which the nuclei gets dissolves and called the embryos, whereas above this critical size the phase transformation takes place or the nuclei grow and then the phase transformation takes place. So, that is a normal phenomena in this kind of a system. It has been explained that AR, a proportionality constant related to the mobility of the interface, R is the variable particle size, PR the terms, whatever terms we have used in this expression, they are actually explained here. Vapor pressure over the particle of radius r, r average, either you call it average particle size or one can say a critical particle size. So, the P average is also the vapor pressure over particle size of radius RAV or R critical. Having discussed that, we just consider the so called grain growth and abnormal grain growth phenomena. In all sintering process, you have a stage where there is a possibility of grain growth, okay, particularly at the final stage of sintering. And it need not say that all the time the grain growth takes place or abnormal grain growth takes place. In some cases abnormal grain growth takes place depending on the system, depending on different other parameters. So, during the final stage of sintering, in addition to pore elimination, grain coarsening takes place. So, that is why we need to consider this. Average grain size increases with time. Larger grains grow at the expense of the smaller ones. That is a very similar phenomena as particle coarsening. Abnormal grain growth refers to a process whereby a small number of grains grow much faster than the others such that their size becomes an order of magnitude larger than the average. Okay. So, few grains, not all grains, few grains grow much faster than the other ones, and as a result their sizes becomes order of magnitude larger than the average grain size. So, that is what we call the abnormal grain growth. This we have seen again earlier, a typical thing in context of the abnormal grain growth. This is what happens. This is the situation where densification has been extended almost towards theoretical density and more than 90%, and then there is a sudden rise in grain size. So, that is what we really call the abnormal grain growth in some cases. Okay. But in general there is a tendency of grain growth, obviously this is coarsening plus densification. So, these are some of the we do not need this, as we have mentioned earlier. This is, there is hardly any, there is a grain growth without densification, that is not a desired situation. This is also not a very desired situation. A more desired situation should be a line like this, somewhere here the intermediate grain size, the theoretical density is achieved. Here theoretical density is not achieved, but the grain size is increasing quite fast. This is somewhere in between. In all ceramic systems, you see less than 90% density is never used, or is not a very useful product. If it is a less than 90% density, it is actually porous ceramics. There are some uses of porous ceramics as membranes. So, there pore size is the criteria, it is not the densification which is not important, or the mechanical strength, although important, but one has to balance how much pores are needed for the material to be used as a membrane, as a sieve, as a microfine porous material. So, there you need larger pores or finer pores in large numbers, but at the same time you need also a strength. So, you have to make a compromise between densification and the mechanical strength, so that the material can be used as a high strength membrane or porous material. So, 100% densification is not always a preferred thing, particularly for membranes, but otherwise very close to 100% densification is certainly a preferred situation. The walls of these large grains may move away from the pores which are trapped within the grains, and thereby do not allow reaching the theoretical density of the solid within a finite time. Now, this is the problem of the abnormal grain growth. When there is a abnormal grain growth, the walls of these large grains may move away from the pores. So, the pores gets entrapped, pores get entrapped within the grains. Normally the pores are supposed to be at the grain boundaries, then the pore elimination is easier, or pore removal becomes easier. So, if the pores are there at the grain boundaries, then pore removal is possible, and one can reach a theoretical density with some finite, within some finite time. However, if the abnormal grain growth takes place, they may entrap during its growth. The grains may entrap some of the pores, and as you have mentioned earlier, they are no longer lenticular in shape, they becomes more spherical in shape, and once they become spherical in shape, that means a more number of grains are actually facing that particular pore, and there is a possibility that they get stabilized. So, there is a possibility that no further pore removal takes place. So, abnormal grain growth also has that kind of problem, that the pores do not get entrapped and do not get the chance to be removed. The process of such abnormal grain growth is also referred to as Oswald ripening. In fact, this was primarily taken from the metallurgical term. Metallurgists use this particular term quite often. The process this is also called ripening of the large grains, and this grain growth is normally avoided if you want to have a better mechanical strength, a better plasticity of the material, and to remove or to avoid brittleness. Normally higher is the grain size or abnormal grain growth, particularly abnormal grain growth of few grains give rise to more brittleness. The phenomena is characterized by a parabolic dependence of grain size on time. So, that is a analysis, mathematical analysis, which gives rise to a parabolic dependence of grain size as a function of time. Well, we have discussed quite a bit on different mechanisms of sintering, different parameters, how they affect the sintering process, how they affect the grain growth, how they affect the densification, whether there is a possibility of stabilization of certain pores under certain conditions. Many different things have been discussed. Let me just go through a kind of summary, a consolidated list of factors influencing the solid state sintering. There are a large number of parameters which actually affects the sintering process. In fact, as we have mentioned earlier, the sintering is always a very complex process. There are many different micro processes which proceed simultaneously, and they affect each other. So, there are a large number of factors which actually controls the phenomena. The most important factor, of course, the temperature, as we have mentioned while we were discussing the rate equations. The temperature, although it is normally in the denominator, but the numerator there is a term, either the vapor pressure or the diffusion coefficient. These are actually exponential terms with exponential function of temperature, and therefore, that those parameters actually dominate so far as the temperature effect is concerned. And temperature, the whole sintering process is a thermally activated process, and therefore, without temperature sintering just cannot take place. We need the thermal activation, the energy, activation energy to be supplied through the thermal process, and therefore, temperature has a very important role to play. However, one also should mention the rate of heating. Rate of heating is another very important issue, because if you increase the temperature too fast, then there may be a particle coalition of particles, what we have seen here, coarsening of the particles, and that may hinder the sintering process. So, rate of temperature rise is also another very important issue during sintering. Vapor pressure and diffusion coefficient we have already discussed, they have also an indirect effect of temperature. The vapor pressure is dependent on temperature, diffusion coefficient is also dependent on temperature, and because sintering involves mass transport. So, these parameters are also of utmost important in diffusion coefficient in sintering process. Initial particle size we have seen in almost all the mechanisms, just like there is a temperature term, there is a vapor pressure and diffusion coefficient term, there is also invariably the initial particle size term, the R term is always there, and it is inversely related to the rate of progress of the sintering process, or the x by r, that is the bond angle, sorry the area, the neck area, growth of the neck area is related to the initial particle size, and generally finer is the particle, greater is the rate, or the higher is the faster is the process. So, you need less time. and not only less time, you also there is more possibility of getting the theoretical density. So, almost all the pores can be eliminated if the particle sizes are finer, and therefore, in ceramics or particularly in advanced ceramics, when you are talking about different kind of advanced ceramics, not the conventional ceramics, in advanced ceramics particle size or particle preparation, powder preparation is a very important parameter or step in getting the dense materials, right. So, there are many different techniques of powder preparation, sometime mostly by solution chemistry route, hydrothermal route, and many different other routes, combustion synthesis route and so on. The idea is to make a finer particle from microfine to now nano size particles. These nano size particles obviously has a faster rate of sintering, and you can get better theoretical density or densification by a sintering process. So, since we are talking about advanced ceramics, this particle size is one parameter which can be controlled and is under our control, and that is normally done by for better property, whether it is mechanical property or optical property or even electrical or magnetic properties. Particle size distribution, not only the average particle size, but the particle size distribution also has a very important role, as almost all ceramists know that the particle size distribution has an important bearing on the initial grain strength or grain density of the material, the particle packing. So, the particle packing can be optimized only through better particle size distribution. Okay. How much fraction of finer and how much fraction of coarse or intermediate are there, that determines the packing density, and better is the packing density, larger is the initial density or initial pore fraction is less, and if you can densify at the room temperature at a larger fraction or to a larger extent, one can certainly get a better density after sintering. Presence of agglomerates need to be avoided. If you have agglomerates, that means a cluster of particles. So, if you have a non-uniform density of the particle or agglomerates, or there are hard agglomerates, there are of course soft agglomerates as well as hard agglomerates. Soft agglomerates normally break under the pressure when you are trying to either dry press or do it by other suspended particle technique and so on, slip casting or tape casting technique. The distribution the particle distribution is very important, or particle suspension. Uniformity of the particle suspension is extremely important. If you do not have uniformity of particle suspension, you may have some agglomerates, non-uniform distribution of particles, and that will immediately lead to non-uniform sintering at different places, at different sites, and ultimately some pores will be trapped. So, pore removal will be extremely difficult if you do not have a uniform particle dispersion in the slip or even during dry pressing, cold pressing, or even isostatic pressing, cold isostatic pressing. So, not only the particle size distribution is important, the agglomerates must be removed, particularly the hard agglomerates. Soft agglomerates can be broken or either during pressing or during suspension, but hard agglomerates obviously have to be avoided. Grain density it is also related to the particle size distribution as well as the grain size, sorry, not the grain size, the agglomerates. So, if you can have a higher green density before sintering at the room temperature, obviously there is a possibility of achieving a better density after the sintering. Uniformity of initial microstructure, once again it is related to some extent to the particle agglomerates. Agglomerates again must be avoided, otherwise the initial microstructure, the pore size distribution, initial pore size distribution will be non-uniform, and that non-uniformity will lead to non-uniform pore structures, and removal of pores will be difficult. Atmosphere of course has an influence because it controls the defect structure of the material, and the defect structure is also very important because ultimately the solid state diffusion is taking place by vacancy mechanism, most of the time it is vacancy mechanism. So, atmosphere also has a very important role to control the concentration of vacancy at different places, and therefore, their mobility also. So, the atmosphere from that point of view is important, but it depends on the particular nature of the material. If it is a non-stoichiometric material, atmosphere has a much greater importance or greater influence. If it is a stable material, it is not so non-stoichiometric material, mostly stoichiometric material, then atmosphere may have a much less influence. Impurities also controls the defect properties, and therefore, the point defects in particular, and therefore, impurities by impurities you can control the sintering process. The impurities also sometimes added intentionally. These impurities lead to some liquid phase formation, and that liquid phase facilitates sintering. I will just briefly discuss the liquid phase sintering because the time is not much there. So, I will just mention about what is liquid phase sintering. Sintering aids, it is also kind of impurities, they go into solid solution or they form interacts with the basic material, and they may form a liquid phase, and that is how help in sintering aids. Both impurities and sintering aids are more or less have the similar characteristics. Either they enhance the diffusion coefficient or increases the vapor pressure or reduces the vapor pressure, or sometimes it forms liquids. So, all of them do have a significant effect on the sintering process. Finally, I will just briefly mention about the liquid. So far we have discussed about the solid state sintering. The liquid phase sintering is also important in many places, many cases. These are the different characteristics. Let me go read out. Sintering in presence of liquid phase, that is what we call the liquid phase sintering. The composition of the starting material is such that it generates a small amount of liquid phase on heating. So, the composition has to be chosen, or sometimes impurities have to be added, or some sintering aids have to be added which forms liquid phase, and of course, the viscosity of the liquid phase is also very important. Viscosity, surface tension and the surface energy, all of them are very important. Also their reactivity with the solid. Okay. All of them normally the liquid is produced in a very small quantities, not even in 1% or maybe within 1%, and then it reacts. Normally it has a very low viscosity and a kind of high capillary action through which the liquid phase moves along the grain boundaries or along the particles interfaces and forms the bond. Liquid should be able to dissolve a small amount of the solid phase and thereby wet the surface of the solid. So, wettability is another very important. Wettability of that liquid with respect to that solid is very important for the liquid phase sintering. So, without wettability the liquid is of no use. So, if a non-wettable liquid is formed, that liquid is certainly not help sintering. In addition to solid vapor surfaces, because you have a additional phase, liquid phase. So, there will be liquid solid as well as liquid vapor surfaces, and those energy terms are also to be considered while we are talking about the liquid phase sintering. Wettability of this liquid phase, as I mentioned just now, liquid has a very important role to play. Capillary forces of the liquid also play a very important role, because in between the grains we have a very some kind of a capillary size of the pores or the openings, and that capillary force also helps in the distribution of the liquid throughout the matrix. In case of liquid phase sintering, the three main stages or main mechanisms which helps in sintering or bonding or removing the pores, these are particle rearrangement, solution precipitation, and in fact solution and precipitation, reprecipitation, and solid state sintering. Towards the end, while the temperature is relatively low, once again the solid state sintering, or sometimes it is called skeleton sintering, takes place. Okay. So, initially particle rearrangement, because in presence of the particle it is much easier for the loose particles to get rearranged and entangled with each other, and some densification takes place immediately, almost immediately. So, that is a very fast process, and then the depending on the composition of the liquid, it dissolves part of the very fine layer of the solid surface gets dissolved, and then it reprecipitates at a within the pores. So, that is another mechanism. Solution and precipitation is another mechanism, and finally, the solid state sintering is also takes place towards the later stage of the sintering process, by the time the densification has already taken place in presence of the liquid, and the liquid, because of the reprecipitation, the liquids will get solidified, and then it will the solid state sintering takes up or takes over. I think this is the last slide, the liquid phase sintering. So, if you plot log time against shrinkage, which is a measure of the extent of densification or extent of sintering, you get a very steep rise first, and then gets flattened out. The shape is slightly different than the other mechanisms. So, this first steep rise takes place because of the particle rearrangement, then the solution and precipitation takes over. It goes, both the things goes together, the particle rearrangement and solution precipitation overlaps, and before the solution precipitation is complete, skeleton sintering also takes place. It is a kind of solid state sintering. So, all these three mechanisms actually occur one after the other, in some cases simultaneously. Two mechanisms takes place simultaneously, and that is how the liquid phase sintering is a very fast process, and better densification sometimes is obtained with liquid phase sintering. So, there are many different examples of liquid phase sintering, particularly in advanced ceramics. Some of them we will be discussing when the actual materials we will discuss at a later class. So, with this we come to the conclusion of the discussion on sintering, and I hope you have been able to give you some idea what exactly the sintering means, how it can be performed, what is the basic purpose of sintering, and what are the different mechanisms by which sintering takes place, and what is the importance of sintering in ceramics, particularly in advanced ceramics. Thank you for your attention.